I hope now my slides are visible. So welcome everyone for today's live introduction session for water and wastewater treatment. And this is the fifth week session. So I am Shaptarshi Bose here, a PMR research scholar from IIT Madras. So as usual, we'll go for the few numerical questions as well as few theoretical questions. We'll try to solve, which will help you for your upcoming examination. And not only that, it will also help you for various kinds of entrance examination, like gate examination or various kind of job examinations. Before starting today's session, I would like to go back the previous session. So one student asked me regarding, just a minute. Yes, one student asked me regarding the transitional flow, laminar flow, as well as turbulent flow. But I made one mistake the last session. So when I told her some value of the Reynolds number to identify whether the flow is laminar flow or it's a turbulent flow, then I made a mistake. Then I thought that there is some mistake, so I checked again and found out, yeah, there was some error from my end. So I want to clarify this. Who will go through this YouTube video, they will also know that the Reynolds number, if it is less than 1, so it indicates laminar flow. And when it is, let me erase this one little bit. When it is beyond 10 to the power 4 values, then it is a turbulent flow. So less than 1 Reynolds number, that will mean that it's a laminar flow. And if the value is greater than 10 to the power 4, then it's a turbulent flow. So this is the range for turbulent flow or the transitional flow. So if the flow is between 1 to 10 to the power 4, then we can say this is a transitional flow. So please keep that in your mind. So it will be helpful. So that's why I uploaded these slides in PDF format with this particular this image. So you can refer to this. This is from a book, a very popular book of environmental engineering. Not only this, I also uploaded another PDF with some theory, basic theory regarding this settling velocities. So type 1 settling, type 2 settling, it will be beneficial for you. So please go through the PDF, which you will find in the Google Drive already uploaded from my side. Please go through that. And if you have any inquiry, please let me know. So up to this was from the previous class. Now I will move to today's session. So the first question is, in the reference to microbial activity, what does endogenous phase refer to? Please use your chat section as usual to write down your answer. Thank you, Murali. I got answer from you. You are saying that is B, right? Okay, fine. So I may wait for a few more minutes for other, like Vavani, and now another new student joined. So I'm telling this to everyone. Please use your chat section to write down the answer. I'll just wait for one more minute, then I will move to the solution because this one is a very easy question, right? Everyone should answer this. Very easy theoretical question. Okay, so the solution is B, correct. Murali, congratulations. So endogenous phase refers to the phase where there is a scarcity of substrate, so food is not that much available, and the population of microbes are decreasing, right? So this is the endogenous phase. Next question, again theoretical questions with multiple correct statements. So please go through it. One or more options correct. So the rate of metabolism of microbes is the lowest in endogenous phase or the system at steady state. In endogenous phase will experience poor settling during secondary settling, or the microbes that thrive during exponential growth phase have good settling characteristics. At the end, F by M ratio for endogenous phase is lesser than that for the exponential growth phase. Okay, I got first answer from Murali. Thank you, Murali. You are saying A and D. Okay, we'll go for the solution. So A and D are the correct answer. So here you can check the rate is very low in case of endogenous phase, but we cannot say that system at steady state in endogenous phase will experience poor settling during secondary settling. We cannot say these microbes that thrive during exponential growth phase have good settling characteristics. But this one is true, right? So this one is already connected to the first question, which we have done. Like there was also one option, right? There's due to scarcity of the substrate, right? So it was related to this endogenous phase. So obviously here F by M ratio for endogenous phase is lesser than that for the exponential growth phase. Why? Because this food is less. This is nothing but F by M ratio, right? A simple thing. So microbes are more and food is less, substrate is less. So endogenous phase, total F by M ratio is low compared to the exponential growth phase. Next one, again, theoretical question, very easy. I already discussed similar question in the last session. Okay, I got again first answer from Murali. You are saying B and C, right? Okay. Anyone else? One more minute. So fine, we'll go for the solution. Yes, the correct answer is you said okay, Bhavani. Thank you, Bhavani, for participating. Right, B and C you are saying. Yes, B and C is the correct one because A and D, like the trickling filter and rotating biological conductors, are the example of attached growth system. These are suspended growth system, right? Or the improvements of the activated sludge process. Or you can say that the improvement or the variation of trickling filter can be said as the rotating biological conductors. The next one related to SBR, sequencing batch reactor. So you have to write down which one is the correct one. The sequence, very easy one. Okay, Murali is saying that C answer. 2 more minutes or one more minute to answer. So yes, C is the correct answer because you can see that here first we are pumping into the uh, reactor, then we are radiating. After that, what we are doing that we are going for the sedimentation. Here the sedimentation is there, and we are decanting the liquid from here. So that is the way decanting. After this decanting, can go for the disinfection. So that is the process. Very simple. So we'll go for the next one, a numerical type question. Please go through it carefully. This is related to activity sludge process, and you can refer to the formula if you have. You can refer to your notes. You can refer to any book. If you can't remember the exact formula, it's fine, but try to solve this. take your time, but try to solve this. So we need to design one activated slash process, and flow rate is Q is given as 50,000 meter cube per day, with influent BOD5 is 250 mg per liter. Decay constant is given as 0.06 per day. The sludge age can be adopted, that is heater sleep, 6.5 days. MLSS concentration in the aeration tank is 2000 mg per liter. So the efficiency of the BOD removal is 35% given. You can assume yield as 0.5 kg per kg. You need to determine the volume of the aeration tank in meter cube. So this is the common data questions for 5, 7, 6, and 7. Write down the data because it will be required for other questions like 6 and 7 consecutive questions. So note it down, all the data. You may not require the exact data for the first question, but you will require in the consecutive questions. The first question is very easy one. You don't need a big formula. I already discussed this kind of question. Okay, I got first answer from Murali, and this is 325000, right? So please be sure with the unit. Right? Okay, no need to wait much. So the first answer is around 5,000, 5,114. You may get something in this range depending upon your calculation. So the formula is this one. I think all of you are aware about this formula. If you have gone through the notes, lectures, that there you will find this formula. I hope that you can understand this formula. I'm not going to discuss more about this from where it was derived and all those stuffs. So I will better say, suggest everyone to refer to the professor's lectures or the notes which are available on NPTEL website. So you will get the better understanding. Because if I want to start again exploring these formulas, it will take time. So basically, this is a very basic formula of this chapter. So please go through it properly because you will require this formula in every steps. So this is very basic one. So like very essential. You cannot skip this formula. You need to remember this. So Vx equals to y q naught multiplied by s naught minus s, that is theta c, divided by 1 plus kd into theta c. I hope all of you know what does it mean, what is this y means, what q means. So V is the volume, that is my required volume, that's what I want to calculate. X is the MLSS concentration, and it was given as 2000 mg per liter in the question. You can refer to the question. So then, and we are finding here V, the value of V we need to find out. Then S naught, that is the BOD concentration, BOD5 concentration 250 mg per liter. Q is given as 50,000 meter cube per day. So here Q naught is 50,000 meter cube per day, and then S naught is 250 mg per liter. The decay constant was given as how much? 0.06 day inverse. So I am writing KD is 0.06 day inverse. Theta C is 6.5 days, right? Then I am getting this efficiency, inlet BOD minus outlet BOD, and divide by inlet BOD. That is what we mean for efficiency, right? So efficiency percentage we can write, or if this is in decimal, fine. So no need to go for the percentage. Efficiency equals to inlet BOD minus outlet BOD. How much BOD is going out from the treatment plant divided by inlet volume. Simple thing. That is 0.35. So the outlet BOD I need to calculate. It will be 1 minus 0.35, right? 1 minus 0.35, I am getting as 0.65 multiplied by 250. 250 was the inlet BOD. I'm getting S as 162.5 mg per liter. Now you just have to put all the values into this equation. So if you put all the values, you are getting something like this: 0.5, 50,000, and 250 minus 162 multiplied by 6.5 days. Then this thing, if you calculate properly, why I am saying properly, because these things were in liter, right? Liter. Here it was in liter. Here the Q naught is meter cube per day. So you need to calculate, or you need to convert the units properly. You have to manage the units properly. If you do that, you will find 5114.66 meter cube is the volume. So the next question, common data question, again you need to calculate if the sludge waste state is V multiplied by alpha kg per day, then what is the value of alpha? So you know what is the sludge waste state formula. I have done this in the last session. So here V multiplied by something was there. So I am writing this as alpha. You need to calculate what is the value of alpha. Just think about the sludge wasted formula. You will get it. I can go back to the data sheet for your reference. Here it is. You can refer to this data paragraph and you can find out. I can again go back to the exact question if you need. Just think carefully. Here we'll go for the solution. Then, so here you can see the correct answer is 0.307. It might be in this range, 6 to 9, depending upon your calculation. Why I said I already discussed this. If you refer to the last session's video, you will find that I already calculated this sludge wastage, right? It was nothing but QWX that was equals to Px by theta c. Theta c is the sludge retention time, theta c, and V is my volume of the aeration tank, and X is my MLS's concentration inside this uh, tank, right? So this is my scenario, and if we are saying that everything is rejected, right? Everything is getting rejected, then suppose this is the scenario: incoming flow, effluent flow, and this is going out. So this is the effluent, this is going out, QW. It might be recycled or it might be wasted, so that we need to figure it out. So I already discussed how theta c is related to this. Theta c is nothing but we can say as Vx divided by QW into XC, and here this is V multiplied by 2000. This analysis concentration X and divided by 6.5, right? 6.5. And this 1000 is to convert the units. So be careful for the units. Take care of all the units. You have to convert it again and again. So I'm getting 0.307 kg per day multiplied by V. So this is my alpha. So alpha multiplied by V it was. So the question was to find out what is the alpha, right? So alpha multiplied by V. We are not putting the value of V here. Just we are trying to calculate what is alpha value. The next one, if concentration of the sludge is 10 kg per meter cube, then what is the recirculation ratio? And this is also a common data question. So if you want the data, I can go back to the previous slide. If you have already noted it down, then there is no need. So here, if the concentration of the sludge in wasted and recirculation both is 10 kg per meter cube, then what is the recirculation ratio? So we'll go for the solution because there is we need to wait a minute. The correct answer is 0.25, and this is how we will try to solve. So the recirculation ratio, I'll again refer everyone to go through the professor's lecture on NPTEL website. So there you will find all the theories, all the derivations, right? So this is QR divided by Q naught equals to recirculation flow divided by influence flow. And from the mass balance, we can write the recirculation ratio equals to QR by Q naught equals to X divided by XU minus X. And if the assumption is theta is much less than theta C. So the hydraulic detention rate time is much lesser than solid retention time. In that case, recirculation ratio. So you know what is the recirculation? If this is my ASP, then some portion is again coming back. So this is how the recirculation is going on in this particular scenario. So this is my ASP, and this way is going inside influent, and this is the effluent, and I am getting this recirculation. So X is the MLSS concentration, that is 2000 mg per liter. So you will put this MLSS concentration here, the place of X. Then XU, how much it was, the concentration in the sludge is 10 kg per meter cube, right? So it was 10 kg per meter cube, and it was multiplied by 1000. I'm getting 10,000 mg per liter, right? So this is XU, 10,000 mg per liter, and equals to 2000. Let me check here. So if you put all the values here, X value 2000, then 10,000 mg per liter minus 2000, I'm getting 0.25. So this is my recirculation ratio, right? And this is nothing but QR. This is the QR properly note, and this is Q naught. So this is the influent flow, Q naught. This is the recirculation flow, that is QR. That much of flow rate is again recirculated inside the ASP. So it is written as QR divided by Q naught. The next question, theoretical question. Which of the following statement regarding the nitrogen removal is correct? Please go through all the options carefully and then answer. More than one might be the correct answers. Now then we will go for the solution. So the B and D is the correct one, that during nitrification alkalinity is consumed. That is true. And if you go for the calculation, I will suggest everyone for the go for the calculation, details calculation from how this nitrogen can be converted, and what for 1 gram of nitrogen consumes 7.14 gram of alkalinity as CaCO2, right? So B and C uh, is the correct one, right? And B and D, right? Sorry. So B and D is the correct one. So B, that is alkalinity is sorry, uh, sorry, this one B and C, right? So during nitrification, we can say that 1 gram of nitrogen releases 7.14 gram of alkyl gas CO2. And also, this will alkalinity will be released in this process. And for this 1 gram of nitrogen requires 4.75 gram of oxygen. So you can go through the nitrification process, how this nitrogen is getting converted, or how we can remove this nitrogen from the wastewater. It might be in the form of ammonia, organic ammonia. Then you can form it as the nitrate, nitrite, and then how can you release this nitrogen? So the next question, again, common data question. Please go through it carefully. Consider a municipal wastewater treatment plant. It uses traditional activity sludge process. Population of the village is 18,000 people. Sewage generation per capita is 200 liter per day. Influent BOD is 220 mg per liter. Sorry. ML VSS concentration is 2,800 mg per liter. Fast order death rate constant, that is KD, nothing but 0.05 K inverse. Specific yield is given as 0.5 mg VSS per mg BOD5 removed. Assume that the PCB enforces the treated wastewater standard of BOD5 equals to 20 mg per liter and the suspended solid of 20 mg per liter. So the first question is, if the volume of the reactor tank is 325 meter cube, then the hydraulic retention time of the wastewater in the tank in hours to achieve the required quality of treated wastewater is, you have to calculate. What is the hydraulic retention time actually required for given volume of the reactor tank, that is 325 meter cube, to achieve your required efficiency. So this efficiency is given by this PCD. It requires the treated water should be having BOD of like BOD5 of 20 mg per liter, not more than that, and the suspended solid can be around this 20 mg per liter. So for this question, uh, I will go for the solution first. So this is the solution here. You need to find out the HRT, right? So Q was given as, how can I calculate Q, the flow rate? The population of the village is 18,000 people, right? And the sewage generation per capita is 200 liter per day. So 18,000 people multiplied by 200 liter per day per capita. So per person, 200 liter of wastewater with sewage is generated per day. So I'm getting as 3.6 mld total flow rate per day. Then the volume is given as 325 meter cube. It was very simple that the hydraulic retention time equals to V by Q. So 325 divided by 3,600. Please be careful with the units. Again and again, I am telling, convert the units. You will find 0.09 days and it can be said as 2.167 hours. Next question, common data question. The average time for which biomass stays in the system in days. Again, you know what does it mean. So I'll go back to the data slide, and from here you can refer all the data. Okay, so we'll go for this solution. So here you know what to find out. That is theta c, so that's solid retention time. So if you go through the material balance for the completely mixed aviation basin, then you will find this formula. I think you know this, you are aware of this formula from your lecture. So please refer to the notes, please refer to the lectures of the professor. You will find that x equals to y divided by 1 plus kd theta c multiplied by s naught minus s multiplied by theta c divided by theta. So theta c I need to calculate, right? Kd decay constant was given as 0.05 day inverse. Theta, which is h at t, I just calculated as here, or it is almost 0.09 days. That is almost 0.1 day. You can write down as S naught to 120 mg per liter, A's as 20 mg per liter, and Y equals to 0.5. X equals to 2800 mg per liter. So if I put 2800 mg per liter equals to 0.5 divided by 1 plus 0.5 multiplied by theta c, and then 220 minus 20 theta c divided by 0.0903. So here you can calculate theta c as 2.896 days. So this is 2.896 days. Just you have to put the data. So this is the MLVSS X value. Then this is the influent BOD concentration. This was the influent BOD concentration, and that was the effluent. That is my targeted, right? 20 mg per liter prescribed by PCB. It is prescribed by PCB. And yield was given as 0.5. Just you have to put all the data in this formula and we'll get it. The next one is the if the microorganisms reach half of their maximum growth rate when BOD5 concentration is 120 mg per liter, then the maximum growth rate is what is the maximum growth rate? If the microorganisms reach half of their maximum growth rate when BOD5 concentration is 120 mg per liter. So the hint is from the Monod's equation. I hope all of you are aware of this Monod's equation and its derivatives. So the actual formula used is S equals to Ks, that is the half concentration. You know this figure. I'm not telling in details. This is my this is my mu m, it is mu m, and this is my Ks, that is the half rate constant, right? Ks, this is half mu half, you can write as mu half. This is mu n, this is the maximum rate constant, and this is the half of the rate constant. And at this point, if you go through this x-axis, this is the food, right, or the substrate axis. This is the rate axis, y-axis, x-axis is the substrate axis. You will find that Ks value is the half position. So Ks is already given as 120. All the other values you know, like Kd 0.05. Then theta c already calculated 2.896. Then mu m, that's what we want to calculate. S was prescribed from the PCB 20 mg per liter, and we are getting this mu m as 2.76. So the next question is facultative bacteria are able to work in which condition? A theoretical question. Please answer quickly. Okay. So the solution is C, the presence as well as absence of oxygen. In both cases, it can work. So that is called facultative bacteria. The next one is the matching of the followings, various terms or various processes with respect to their descriptions, anoxic, heterotrophic, anaerobic, autotrophic. Please answer this quickly. So we'll go for the solution. The correct answer is B. Yes. So you can see here, anoxic system is the, we'll go for different things. So we will know, try to know different descriptions. What does it mean by this term, right? So yes, yes. Anyone wants to contribute? Yes. If you have any doubt, okay. So I think this is clear for everyone. Yes, like that is the correct one. So the anoxic, where we see absence of oxygen only, and heterotrophs, we are getting that it is those microorganisms which are obtaining energy and material from the organic sources. In case of autotrophs, what we can find, this is the obtaining energy and material from inorganic sources. These are the difference. Heterotrophs are getting from organic sources, and autotrophs are getting from the inorganic sources. And then this anaerobic system is the absence of electron acceptors, like not only oxygen. Be careful with this anaerobic system. Also, nitrates or nitrite, all the forms which can have these electron acceptors, that they are not present there inside the system. So that system can be called as anaerobic system. Not only oxygen. Popularly, we think about only the oxygen, but not only the oxygen. All kinds of these kind of the electron acceptors like nitrate, nitrite, and all. So then, thank you. That was the last question. Thank you everyone for joining today's session. Hope you enjoyed and also learned many things. We will meet in the next session on next Tuesday. Thank you everyone for joining this session. So you may leave now. Thank you everyone.